We can also solve for the values of K and for the values of Q to be able to predict whether the reaction system will proceed to the product side or the reaction system will proceed to the reactant side. Let's try this with the problem solving. So this is the problem. At the start of a reaction, there are 0.249 mole of nitrogen, 3.21 times 10 raised to negative 2 mole of hydrogen, and 6.42 times 10 raised to negative 4 moles of ammonia. This is present in a 3.50 liter reaction vessel at 375 degrees Celsius. So if the Kc for the reverse reaction, 1 mole of nitrogen gas plus 3 moles of hydrogen gas can produce the product of 2 moles of ammonia gas is 1.2. At this temperature, decide whether the system is at equilibrium. If it is not, predict which way will the reaction will proceed. We have the given values for nitrogen is equals to 0.249 moles, hydrogen is equals to 3.21 times 10 raised to negative 2 moles, and ammonia is equals to 6.42 times 10 raised to negative 4 moles. The volume is 3.50 liters. The Kc or equilibrium constant is equals to 1.2 and the temperature is equals to 375 degrees Celsius. Now, for the first step, we must always remember that in order to solve for Q or K in the given problem, the given value should be present in concentration or molarity. Notice that the given are present in moles, so we have to calculate for its molarity. Molarity can be solved by the formula M is equals to moles of solute over liters of solution. Now, we get the molarity of each species starting from nitrogen. Molarity of nitrogen is equals to 0.249 moles over 3.50 liters. That would give us the result of 0.071 molarity. Next is for the molarity of hydrogen. For the molarity of hydrogen, we have 3.21 times 10 raised to negative 2 moles over 3.50 liters. This would give us 9.171 times 10 raised to negative 3 molar. And lastly, for the molarity of ammonia, we have 6.42 times 10 raised to negative 4 moles over 3.50 liters, which should give us the result of 1.83 times 10 raised to negative 4 molar. Calculating for the molarity of each species, we now have to find the value of Q. Our Q is now represented by this equation. Q is equals to quantity ammonia raised to 2 over the quantity nitrogen times the quantity hydrogen raised to 3. Then, we have to put the molarity values from earlier to the given equation. So we have now Q is equals to the quantity 1.83 times 10 raised to negative 4 raised to 2 over the quantity 0.071 molar times the quantity 9.171 times 10 raised to negative 3 molarity raised to 3. Calculating that, we would have 0.6115 as our Q. Finally, we both have the value of K and Q, so we can be able to tell its direction. Note that K has the value of 1.2 and Q has the value of 0.6115. Comparing K and Q, we have concluded that K is greater than Q, and therefore the reaction directions is to the product side, which is product favor.
First, we will use the ice table where we have the initial molarity of fructose, which is 0.244 and 0 for glucose. For the change, negative 0.131 for fructose and positive 0.131 for glucose. At equilibrium, fructose is at 0.113 molars and glucose is at 0.131 molars. For the equilibrium constant, use the product over reactants. Therefore, we have glucose over fructose. Substitute the values. After that, we will get the equilibrium constant of the reaction, which is 1.16. To get the percentage of fructose converted to glucose, percent of fructose converted is equals to the amount converted over the initial amount multiplied by 100. Substitute the values and we will get 53.7%.
Here's another problem. Pure phosgene gas, COCl2, 3.00 times 10 to the power of negative 2 mole, was placed in a 1.15 liter container. It was heated to 800 Kelvin, and at equilibrium, the pressure of carbon monoxide was found to be 0.497 atmosphere. Calculate the equilibrium constant, Kp, for the reaction carbon monoxide gas plus chlorine gas are in equilibrium with phosgene gas. You may pause the video now if you would like to solve it on your own. Here's a step-by-step on how to solve this problem. Firstly, identify all the given. 3.00 times 10 to the power of negative 2 mole of COCl2, 1.50 liter, which is the volume, 800 Kelvin, which is the temperature, 0.497 atmosphere, which is the equilibrium pressure of carbon monoxide. The thing that we are asked to find is the equilibrium constant Kp for the given reaction in the problem. For the first part of the solution, we must first calculate the initial pressure of COCl2 using the ideal gas equation, PV equals nRT. We are finding the pressure, so we just need to divide the volume for each side, cancelling the volume on the left side and making the final equation P equals nRT over V. Recall that the value for R, or universal gas constant, is 0.0821 liter times atmosphere over mole times Kelvin. Now, we just need to substitute the values that we have. Pressure of phosgene gas, which is unknown, is equal to the mole of phosgene gas times the value for R times the value of the temperature over 150 liter, which is the volume. Cancelling all the same units, we are left with atmosphere, which is the unit for pressure. Solving the equation, we have 1.3136 atmosphere, the initial pressure of COCl2. We are not done yet because what we just solved is just the initial pressure of COCl2. Next, we must use the ICE table to tabulate the changes in pressure. Initial pressure of CO and Cl2 is 0 because the container only contains phosgene gas. The initial pressure of COCl2 is 1.3136. Since the reactants are equal to 0, the reaction must shift to the left, so both CO and Cl2 will increase by X, making COCl2 decrease by X, based on their mole ratio. Combining the initial and change values, we would get the equilibrium. But how do we find X? The pressure of carbon monoxide in the table is X. Going back to the given, you would see that the equilibrium pressure of carbon monoxide is already given. Because of this, X now is equal to 0.497. Therefore, also making the pressure of chlorine gas to be equal to 0.497. We just need to replace all the X with 0.497. Lastly, we just need to substitute the values to the equilibrium constant expression. Kp equals pressure of COCl2 over pressure of CO times pressure of Cl2. Input the values, 1.3136 minus 0.497 over 0.497 squared because they both have the same value. Solving for the equation results in 3.30595241. Therefore, the final answer would be 3.31, minding the significant figures.
So since pH plus POH is equals to 14, POH is equals to 14 minus yung pH, which is 10. So 14 minus 10 is equals to 4. So ito yung POH natin. The hydroxide ion concentration is equals to 10 raised to negative POH or 10 raised to negative 4 is equals to 1 times 10 raised to negative 4m. Since ang sodium hydroxide ay isang strong base, it ionizes completely. Its initial concentration is equal to the concentration of the hydroxide ion. So, kailangan natin mag-prepare ng 546 ml of 1 times 10 raised to negative 4m or 1 times 10 raised to negative 4 mole per liter sodium hydroxide solution. To solve for the grams of sodium hydroxide needed, we will do dimensional analysis. From the concentration, we will find the moles of sodium hydroxide, then we can solve for the grams. We know that 546 ml is equals to 0.546 liters. We will multiply it by the concentration to get the moles. So 0.546 liters times 1 times 10 raised to negative 4 mole per liter ng sodium hydroxide. Then, multiply by the molar mass of sodium hydroxide to get the grams. So ita-times natin to sa 40 grams per mole is equals to 2.18 times 10 raised to negative 3 grams of sodium hydroxide needed.
Bago tayo magtungo sa ating solving part, we shall know that H2C2O4 or the oxalic acid is a diprotic acid, which means meron siyang dalawang acidic protons, which is the H2 here, na pwede niyang i-donate sa ibang atoms. With this, magkakaroon tayo ng dalawang chemical equation. Unahin muna natin is yung oxalic acid, which is the H2C2O4 in aqueous solution, is at equilibrium with hydrogen ions in aqueous solution plus HC2O4 negative or the hydrogen oxalate ion in aqueous solution. First thing to do to solve this problem is to create an ice table, which is the initial, change, and equilibrium table. The only quantity that is given in our problem is the concentration of our oxalic acid, which is 0.20 molars. So next is denote natin yung ating change in equilibrium using variable x. We will subtract it on our reactant side and add it on our product side. So sa ngayon, makukuha na natin yung denoted value ng mga concentrations ng ating reactant and product at equilibrium. So yung concentration ng ating oxalic acid is denoted as 0.20 minus x, and yung hydrogen ion naman natin and yung hydrogen oxalate is denoted as x. We can now solve for the values of x using the equation of our ionization constant, which is Ka is equal to the concentration of the products, the hydrogen ions, and the hydrogen oxalate over the concentration of our reactant, which is the oxalic acid. So kanina, ipinakita na natin ang value ng Ka ng oxalic acid, which is equal to 6.5 times 10 raised to negative 2. We can now substitute yung mga values na meron tayo sa ating equation, which is 6.5 times 10 raised to negative 2 is equal to x times x all over 0.20 minus x. Pwede na tayong mag-cross multiplication dito, which will make our equation as 6.5 times 10 raised to negative 2 times the quantity of 0.20 minus x is equal to x squared. Further simplification sa ating equation will lead us to x squared plus 0.065x minus 0.013 is equal to 0. Pwede na nating masolve yung values ng ating x using quadratic equation, which is 0.086 and negative 0.151. The x sub 2 can lead us to a negative concentration, which is not possible, so we should cancel this out. Pwede na natin ngayon is-substitute yung ating value ng x to get the concentration of the reactant and our product. Makukuha natin yung concentration ng ating oxalic acid, which is equal to 0.114, and yung ating products, which is the hydrogen and hydrogen oxalate ion, which is equal to 0.086. Para sa ating pangalawang chemical equation, which is HC2O4 negative, o yung ating hydrogen oxalate ion kanina, in aqueous solution, is at equilibrium with H plus in aqueous solution plus C2O4, 2 negative in aqueous solution, o yung ating oxalate ion. Upon solving kanina, nakuha natin yung initial concentration ng ating hydrogen oxalate ion and yung ating hydrogen ion which is equal to 0.086 molar. So ngayon, i-denote naman natin yung ating change in equilibrium using the variable y. This will lead us sa concentration ng ating reactant and product at equilibrium which is equal to 0.086 minus y for our oxalic acid, 0.086 plus y for hydrogen ion, and y for oxalate ion. Just like kanina, i-use din natin yung equation ng ating ionization constant which is equal to the concentration of our products over the concentration of reactant. Given din yung value ng ating ionization constant, so i-substitute lang natin ito sa ating equation. This will lead us to 6.1 times 10 raised to negative 5 is equal to 0.086 plus y times y all over 0.086 minus y. Again, applying cross multiplication will lead us to 6.1 times 10 raised to negative 5 multiplied to the quantity 0.086 minus y is equal to the quantity of 0.086 plus y times y. Further simplification ng ating equation by distributing the values inside the parentheses and combining like terms will lead us to the equation of y squared plus 0.0860061y minus 5.246 times 10 raised to negative 6 is equal to 0. Again, using the quadratic equation will lead us to the values of y of 6.091 and negative 0.086. Both of these values can lead us to a negative concentration, which is not possible, so we should cancel this out. So because of this, na both yung values ng ating y will lead us to a negative concentration, nagagamit naman tayo ngayon ng approximation. So 6.1 times 10 raised to negative 5 is equal to 0.086 plus y times y all over 0.086 minus y. This means that we will approximate the values of 0.086 plus y and 0.086 minus y is also equal to 0.086. Using this equation, pwede na nating ma-solve yung value ng ating y which is 6.1 times 10 raised to negative 5. So to sum up yung mga values or answers na nakuha natin kanina, yung first, yung ating H2C2O4 or oxalic acid is equal to 0.11 molar. Ang ating HC2O4 negative or ating hydrogen oxalate is equal to 0.086 minus y or 6.1 times 10 raised to negative 5 is equal to 0.086 molar. Yung atin namang hydrogen ion is equal to 0.086 plus y or 6.1 times 10 raised to negative 5 is equal to 0.086 molar. Lastly, yung ating oxalate ion or C2O4 negative is equal to y which is 6.1 times 10 raised to negative 5 molar.
First, we start off with solving for the pH of the ammonia. We need to make an ICE table for the equilibrium first, which is NH3 plus H2O, which creates NH4 and OH. Starting with the initial concentrations of 10 molars for NH3, 0 for NH4 plus, and 0 for OH minus. The change values would be minus X for NH3 and plus X for NH4 and OH minus, which would have our equilibrium be 1 minus X for NH3 and X for both NH4 plus and OH minus. The Kb for the equation is NH4 plus times OH minus over NH3. The Kb value of NH3 is equals to 1.8 times 10 raised to the negative 5, which would give us 1.8 times 10 raised to the negative 5 equals x times x over 0.10. This turns to x squared equals 1.8 times 10 raised to the negative 6. Then we will apply square root to both sides to get x equals 1.34 times 10 raised to the negative 3. This will be used to obtain the power of hydroxide. Power of hydroxide equals negative log 1.34 times 10 raised to the negative 3. which equals to 2.87. And now we can get the pH by subtracting our POH from 14, which equals to 11.13. We will use the same way of solving for the pH of ammonia to also solve the pH of pyridine, but we will use the molar and Kb of pyridine instead. Kb equals C5H5NH plus times OH minus over C5H5N. The Kb value of C5H5N is 1.6 times 10 raised to the negative 9. That would give us 1.6 times 10 raised to the negative 9 equals x times x over 0.050, which turns to x squared equals 8 times 10 raised to the negative 11. Then we will square root both sides to get x equals 8.94 times 10 raised to the negative 6, which we then insert into the POH equation. POH equals negative log 8.94 times 10 raised to the negative 6, which equals to 5.04. Subtract 5.04 from 14 to get the pH, which is 8.96.
Now let's do calculations about acid-base titrations. So the hint here is yung HIN or phenolphthalein and ion negative ay at equilibrium due to the indicator color changes at this point. So ion negative over HIN or phenolphthalein is equal to Ka or dissociation constant over H plus na mag-equal sa 1. So bakit 1? Lagi nating tatandaan na when reactants and products are at equilibrium, mag-equal sila lagi sa value na 1. And after that, both H plus and Ka ay equal sa 2.0 times 10 raised to negative 6. And using the formula pH is equal to negative log multiplied to H plus, magiging pH is equal to negative log 2.0 times 10 raised to negative 6. And doon tayo mag-arrive sa ating final answer na 5.70 pH level.
Calculate the pH at the equivalence point for the following titration: 0.10 molarity of HCOOH versus 0.10 molarity of NaOH. In this problem, we will assume 1 liter of formic acid and 1 liter of sodium hydroxide. Computing for the number of moles, this gives us 0.10 mole of HCOOH and 0.10 mole of NaOH. Then we write the balance equation, which is when HCOOH is added with NaOH, it produces HCOONA and water. Based on the given, we initially have 0.10 moles of HCOOH and 0.10 moles of NaOH. And when this reacts, it will form 0.10 moles of HCOONA. The H2O will be ignored as it is in liquid form. The reactants will be 0 since HCOOH and NaOH is a strong acid and base respectively. After this, we calculate the molarity of HCOONA, which is 0.050 molar. The pH at the equivalence point will be calculated through the hydrolysis of HCOO ion, which is a weak base. In the ice table, we start with 0.050 molar of HCOO ion. Then let's assign the X interchange, the negative for the reactant and positive for the products. The water will again be ignored. To find the value of X, we will use the formula for the ionization constant. Kb, which is the base dissociation constant, is equal to products over reactants. Since Kb is constant, we know that the Kb of HCOONA is 5.9 times 10 raised to negative 11. Then we substitute. We assume that 0.050 minus x is approximately 0.050 since the value of x has a small value. Using our calculator, we find that the value of x is equal to 1.7 times 10 raised to negative 6 molar. So, the x here is the molarity of the hydroxide ion. Then the value of POH will be 5.77. Then, to find the value of pH, we subtract it from 14 and we have 8.23. Therefore, the pH at equivalence point is equal to 8.23.